the last required topics of the course, convection, is discussed in Chapter 6 and in Chapter 7, mostly addressing forced convection topics for external flows. There are other situations, internal flows and natural convection, that are simply left for you to explore yourself later on and as needed in later courses or as an engineer. So this is your last homework assignment number 8. You have some readings assigned. Be aware that as you go through those readings, there is a coupled discussion, mass transfer and heat transfer. By convection, you're only responsible for the convection, the heat transfer part of that. So that's your selected reading from Chapter 6 and homework assignments, 5 homework assignments. And Chapter 6 is more of an introduction to the concepts and the necessary math that govern the convection problem. Chapter 7 is finally when we start looking at some of the correlations and solutions for the heat transfer coefficient. Chapter 7, that is. So there's some reading in Chapter 7 and then some homework problems in Chapter 7. So we're going to address Chapter 6 and Chapter 7. This lecture will only address Chapter 6, and then we'll have a couple of lectures on Chapter 7 to conclude the required content of the course. Okay, so let's talk about convection, which really means how do we come up with the heat transfer coefficient H? How do we come up with an actual estimate, a good estimate for H? Back in Chapter 1, we introduced Newton's law of cooling and the heat transfer coefficient H, and then we're always given a value. Well, it turns out that that value is very, very dependent on the flow field, and it's actually kind of a complicated problem to come up with an H value that is accurate. So Newton's law is accurate if you have a good estimate for H. So let's think about this as a local analysis. The heat transfer, Newton's law of cooling, actually occurs at every single point on a surface. So we can think about this as a flux, and that H being a local measure, same as this surface, Q double prime, the flux varies over this entire surface. So there is a varying H depending on the flow situation at that very point. So what's important, what's influencing H, is the flow field very close to the surface. So what's causing there to be a flow field, though, is some upstream source, some V upstream or U ambient, meaning what's the velocity, the free stream velocity far away from the surface. So there will be, I guess you remember, a no-slip boundary condition from fluid mechanics and a boundary layer and a lot going on close to this surface. Okay, so more about that later. Next, to figure out what the total heat transfer Q is, we need to integrate that flux, which can vary over the surface, right? So we'll take the expression for Newton's law of cooling, put it in place for the flux. So now we have to integrate H times the temperature, which is not necessarily an isothermal surface. So the temperature can vary as well all over the surface. Now I'm using X here kind of generally to be position. It is X when we're talking about a distance from the leading edge of a flat plate. The X will tell us what the position is. Okay, so if we have an isothermal surface, for example, maybe this is metal or a highly conductive material, so heat transfer laterally, there's very little resistance to that compared to normal to the surface, so we maybe can expect that to be isothermal. Oftentimes that is the case, very often that is the case. So if it's isothermal, then T is a constant. Ts minus T ambient is a constant, can come outside the integration. So we're left with this, the integral of H dA. So now if we define the average heat transfer coefficient, just with the common definition of an average, H bar is equal to the integral of H over the area divided by the area. Then we can replace this integral expression with H bar times the area, which gives us HQ equals H times A times delta T. This is what we were introduced as Newton's law of cooling in Chapter 1. So previously we called that H and didn't distinguish between a local or an average value. Well, it turns out in chapter 1, H was the average value. So now we're going to distinguish a local from an average. H bar means the average H over an entire surface. What surface? This surface area. And H bar will mean and H will be the local. So I'm writing it here as H is a function of X just as a reminder of that, and that H bar is the average heat transfer coefficient. Okay, so the fluid flow, as I said, dictates what that H is going to be, which makes this kind of a challenging problem to calculate values for H. For example, there will be a laminar region of flow at the near the leading edge of a flat plate, for example, where if we had a uniform parallel flow coming in over this plate, that would be laminar for a while, and so streamlines are collinear and moving along in this direction, and at some point the flow becomes unstable and you get little vortices, little gushes of flow up, backwards, and around. On average it's still moving forward, but this is a turbulent region. So in this region, mixing of flow dominates over here, diffusion dominates, so there's different physics going on. H is drastically different between these two regions. In more complicated flow situations, flow around a cylinder, for example, you might have the laminar boundary layer region here, and then that boundary layer becomes turbulent, and then maybe at some point the boundary layer separates and you have a wake region, so now there's even a larger variation in the physics that's going on. So you almost need, if you're going to solve this for H using a correlation, you almost need a different correlation for all of those regions. Let's consider the boundary layers that are important here. If you remember from your fluid mechanics course, as a flow passes a solid boundary, there's the no-slip boundary condition. So the fluid right next to the surface is not moving relative to the surface. Right at the edge of the boundary layer, so at this point, the flow is 99% of the free stream velocity. U ambient is the free stream or the upstream velocity. So outside the boundary layer, the velocity, the U component of velocity is U ambient. Inside the boundary layer, there's a momentum deficit, and so the velocity distribution or velocity profile curves back to zero. And this is what it looks like. It looks like a curve like this. So the edge of the boundary layer, where U is equal to 0.99 of U ambient, is called delta. So delta is this distance from the plate to the surface, to the edge, and that is going to grow starting from the leading edge where it's zero. The boundary layer grows moving to the right. So all of this is part of the solution for the flow field. So the Navier-Stokes equations and continuity govern the flow field out here. But all of these are just characteristics that are observed from the solutions. Okay, so there's also a thermal boundary layer as well, far enough away from the surface that's at Ts, so let's assume T surface is higher than T ambient. Far enough away, the fluid is at a temperature T ambient. Right next to the fluid, directly adjacent to the surface, the fluid temperature is the same as that of the surface. So there's a transition between those two that occurs over a thermal boundary layer. So for the thermal boundary layer, we call that delta sub T for the thermal boundary layer. At the edge of the thermal boundary layer, T is equal to 0.99 of T ambient. So this is a profile of the temperature as it varies in the y direction at this particular x location. So x is the distance from the leading edge. So if you remember the Reynolds number from your fluid mechanics course, so that would be rho times U ambient times a distance L divided by mu, the viscosity. That's a dimensionless parameter. If the Reynolds number for this flow is very, very large, then that suggests that there will be a boundary layer. Inside the boundary layer, viscous forces are important and they balance inertia. Outside the boundary layer, we can assume the flow is inviscid, and Bernoulli's equation would apply out here. So again, different physics in that situation as well. The Navier-Stokes equations govern the flow field here. There is actually an energy equation that governs the temperature field here that is coupled with the velocity field. The governing equations are continuity then and the Navier-Stokes equation. Navier-Stokes represents balance of linear momentum locally. So I've written these in linear algebra notation. That's the full derivative. I'm sorry, that is the material derivative. If you remember, the material derivative has a local acceleration and a convective acceleration component. So these are nonlinear equations. The gradient, the pressure gradient affects the solution. This is the viscous term, and this is a body force term. So all of this contributes to a momentum balance of a fluid particle and governs how that particle moves around. Continuity, this for incompressible flow is divergence free. And then finally, here's the heat equation, or the energy equation is basically the heat equation now, but with a moving fluid. So here's the same diffusion term you're used to. This looks like the energy storage term, right? And so if you looked at the first part of that material derivative, that would be the energy storage term. But then you also have these advective terms that would show up in this equation. So this also is a nonlinear second order equation. There is a viscous dissipation term, so this is basically friction. So because of the viscosity in the fluid, it causes the temperature of the fluid to increase very slightly. Normally this can be neglected except for at high velocity gradients. And then this is that same energy generation term you're used to. Alright, so these governing equations apply at every single point in the flow field. Navier-Stokes over here in continuity, and then the energy equation over here. And so the existence of a boundary layer is actually part of the solution. It's not explicitly noted, it's just part of the solution. So the governing equations are nonlinear. They have boundary layers internally. Second order partial differential equations, spatially second order, first order in time. So we need an initial condition, we need boundary conditions around the entire outside of the domain for the spatial derivatives. Steady solutions, so steady just so they don't depend on time, can be laminar. They can also be unstable depending on the situation. So turbulence is an extra burden to worry about. The velocity field dictates the temperature field, so they're kind of coupled together. However, if you assume the viscosity and the density don't depend on temperature, then you can actually solve for the flow field separate from the temperature field, and then once you have the flow field, use that to input into the energy equation to solve for the temperature field that way. So the solutions involve property values that can depend on temperature, surface conditions, surface roughness can sometimes be important, the geometry, obviously, boundary layers, turbulence, and whether or not you're internal or external flows. You can have forced convection or natural convection. Many, many different physical situations that are going on to figure into the flow field that affects H. Solution techniques. For some cases, laminar cases, you can solve for it analytically, sometimes even analytically, and maybe some hybrid of numerical, like we'll see for a flat plate, or they just need to be solved numerically. Numerically means computational fluid dynamics, CFD, which is almost effectively an entire field itself. It's very, very challenging to solve the Navier-Stokes equations, but if you can do that accurately, you can use the flow field if you solve for the temperature field as well. To figure out what H is. Computationally expensive and takes a lot of time and effort to put that together to come up with those solutions. The popular kind of even more convenient way to do it is to solve this experimentally. Set up an experiment, calculate the heat transfer, or calculate the temperature differences, and measure the heat transfer, and then use that to calculate back calculate an H value. So that's the popular way to do it. We're going to use correlated solutions that were arrived at with experiments mostly in this class. So that is called the problem of convection. Then is how to come up with appropriate values for H and H bar for the particular flow of the engineer's interest, for the particular flow, geometries, whatever's driving the flow, that whole situation. And so this is called also the heat transfer problem, or the problem of heat transfer, because it is still the one area of heat transfer left where there's a lot of active challenge and research going on. There's a lot still to be learned into how to estimate this H value. The same really can't be said for radiation or for conduction for that matter. Those physical laws are very well understood. But coming up with values for H in Newton's law of cooling is still a challenge. Okay, so let's talk a little bit more about the flow characteristics. Without knowing the solutions, there's a lot of observations and things that we can make. So let's talk about the velocity field first, and the boundary layer, and this velocity profile, and what we expect. What are some of the conclusions we can make from this? So first of all, this existence of a boundary layer occurs only for a very, very large Reynolds number. So remember the Reynolds number based on L. Let's call the entire length from the leading edge all the way down to the trailing edge of this plate. So let's assume the plate ends right there. That distance is L. So now the Reynolds number based on that length L is rho times U ambient, this upstream velocity, times L divided by mu, dynamic viscosity. So that has no unit. So if you put those together, so you calculate a value of the Reynolds number. For a very, very low Reynolds, in fact, in the limit as the Reynolds number goes to 0, there is no boundary layer. This boundary layer gets larger and larger and larger until it finally disappears. So it raises up this way until there is no boundary layer. For low Reynolds number flow, viscosity is important everywhere. For high Reynolds number flows, though, the larger the Reynolds number, the smaller this boundary layer is, or lower the boundary layer moves, I guess. So for a higher Reynolds number, the boundary layer would be down here, for example. Right, so that's a larger Reynolds number implies a smaller delta as a function of x. Should put a little L there for that. So notice that as the velocity increases, the Reynolds number therefore increases, and you can imagine that will push the boundary layer to be smaller like that. There is a shear stress occurring in here. If you remember from fluid mechanics, shear stress is mu du dy. So this flow does cause there to be a shear stress on this surface. If we didn't have a force on this plate, the plate is not going to stay here. So there's a shear stress acting that way on the plate. So tau sub s for shear stress on the surface, or tau shear maybe, is actually going to vary with x, the position from the leading edge. So on that boundary right there, that tau shear is actually equal to mu times the derivative of u, that velocity profile, with respect to y. Evaluate that at y equal to 0 multiplied by mu gives you the shear stress on the wall. Okay, so the larger this slope, so this slope right here, the more shear. Larger slope, partial of u with respect to y, implies larger shear. And then ultimately, if you add up that shear over the entire surface, a larger force to hold the plate in place, or a larger drag force. So this drawing is u at a particular x distance as a function of y. Alright, so that's the profile. You have to specify at what x distance from the leading edge for that profile, and then the boundary layer is u at y equal to delta is equal to 0.99 of U ambient. So you got to pick something as the edge of the boundary layer. So another observation, or we already made one observation, that as increasing the Reynolds number, this boundary layer is going to decrease. So imagine decreasing this distance over which U has to vary between 0 and U ambient. If you decrease that, that's going to increase the slope here. If you can imagine that curve is still going to be here, right? But as you shrink down this distance, that curve is going to occur. It's going to be a higher concentration effectively, so it'll be a higher slope. So increasing the Reynolds number implies decreasing delta, which is then increasing that gradient at y equal to 0, which will then increasing tau surface. So in increasing the Reynolds number, you can do that several ways, but one is by increasing the velocity here. If I increase that velocity, we are then increasing the shear stress and thus the ultimate drag force on the plate. Another observation I want to make from this is if we consider the variation in the x direction. Right, as we increase in the x direction, the boundary layer increases, so therefore that gradient is decreasing as you move in the x direction. So this shear stress then should be decreasing as you move in the x direction. So at larger x locations, partial of U with respect to y at 0 is decreasing. So that's going to imply a decreasing shear. So as the boundary layer shrinks, because the Reynolds number is increasing, the shear is going to increase. But still, as as you move from the leading edge this way, the shear stress is going to be decreasing because of an increasing boundary layer. The boundary layer grows as you move down the plate. Okay, so we can make a lot of similar observations about the thermal boundary layer. Alright, the thermal boundary layer, so this entire line all the way along here is, if you substitute into a temperature profile theta T for Y, by definition that's 0.99 of T ambient. That plot is T as a function of Y. Again, is the profile at an X value. It's drawn here as if T surface is greater than T ambient. Of course, it could be the other way around, right? It could be T ambient is larger than T surface, in which case it will just curve back this way. Okay, I want to think now, so we had the shear stress we could talk about up there on the surface. Here we have a energy balance that we can talk about on this surface. So the surface energy balance, so let's think about the layer of fluid that's right here that's not moving because it's right next to this surface. It has energy conducting through it, right? There's some conduction and then it's convecting away on the other side. So let's do a surface energy balance right on that layer of liquid. What's conducting through the liquid is minus K of the fluid. I guess it's not necessarily liquid. K of the fluid times the partial of T with respect to Y at Y equal to 0. That has to equal to H TS minus T ambient. Surface energy balance. Alright, so that's what's occurring right on the surface. Right, the bottom layer of liquid is static. no slip boundary condition. So let's put also right there, U at y equal to 0 is equal to 0. No slip. That would be one of the boundary conditions imposed when you're solving the Navier-Stokes equations for the velocity field above. Okay, so I do want to point out that this K is not of the solid. That is of the fluid. That's why I put a little subscript F. They don't always have that in the textbook. That K is actually now of the fluid, not of this solid material, because this energy balance, this surface energy balance, is of the liquid that's not moving, right? That's where we're deciding to draw this, because that's where our boundary now is. What's going to govern H is the fluid flow, right? Not this solid surface. Okay, so now we can make similar observations. The first one would be increasing the Reynolds number. Alright, so if we increase the Reynolds number, that will, just like for the velocity field up above, that's going to decrease delta for the thermal field as well. So it decreases the boundary layer, thermal boundary layer. If we increase Reynolds number, then we'll have a decreasing delta T, right? This follows delta because the flow field and the temperature field are coupled, right? And so then we're going to have an increasing gradient on this surface as we lower delta, increasing the partial of T with respect to y at y equal to 0. Alright, so if I increase this term increases, that's going to cause an increase in H. So we'll have an increasing heat transfer coefficient, H. So as complicated as the flow field and thermal field are to solve with those governing equations, H only shows up on the surface boundary condition of the thermal energy for the thermal energy equation. Okay, so there is H here. So if we increase the Reynolds number, so cause that boundary layer to be smaller, we're going to increase H. Now let's think about what happens to H for the case as we move downstream. So at larger X values, the thermal boundary layer is growing, right? So as the thermal boundary layer is growing, the partial of T with respect to y at y equal to 0, so down here on the bottom, is actually going to be decreasing. We have a lower slope. So that would be a decreasing. If this number is decreasing, that's a decreasing H, all the other numbers being the same. So we have some idea about what to expect from the trends in the solutions that we would get from either our empirical experimental results or from solving the Navier-Stokes equations numerically. Okay, so we've already presented enough that we can kind of talk about your homework problems for Chapter 6. So let's do that kind of before we move on. This first one, number 1, is actually talking about effectively the discussion we just had. The boundary layers. So they've drawn a boundary layer situation. This is the thermal field because you see these are temperature profiles here and here. So there's a uniform temperature profile before the effect of the plate is here, right? As the fluid is now passing by, a temperature profile farther down here, right, is now going to have to vary between T ambient down to the temperature of the surface. And so here you can see T ambient is larger than the temperature of the surface for this particular situation through this profile. So that's the answer to the first question. Is the plate being heated or cooled? Right? In this case, the plate is being heated. Carefully sketch the temperature distribution at positions 1 and 3. So we have a position x1 up here, right, where the boundary layer is very, very short. So over this distance, we have to vary from Ts to T ambient over that small vertical change. Here it happens over a larger vertical change. If you go down here to x3, you're going to draw it here as well. You go to an even larger change. That same shape, though, it'll look just like this same shape, just scaled up or scaled down. Based on your sketch of those 3 locations, at which one of these would the local heat flux be the largest? Where would the heat flux be the largest? Where there's the largest temperature gradient, it would be the largest, right? And so the largest gradient would be, you had the same delta T for all of these, right? A larger gradient is where that delta T occurs over a smaller distance. So this would be the largest heat transfer at x1. Right, so the heat transfer rate is decreasing as you move to the right. So H also then is decreasing as you move to the right because delta T is the same. At which point would it be the smallest? Okay, so it'd be at the far right side for the smallest. As the free surface velocity increases, the velocity and thermal boundary layers both become thinner. Okay, so now they're thinking about the case where as you increase that upstream velocity, that free stream, the boundary layers now move downward. So that would be the drawing that I said earlier. For a larger Reynolds number, the boundary layer is going to be down here rather than up there. The larger it gets, the smaller that boundary layer is going to be. Carefully sketch the temperature distributions at 2 this time for that smaller boundary layer, and then for 1 for a lower free stream velocity, and then do it again for a higher free stream velocity. So for a lower free stream velocity, the boundary layer is going to rise and it'll be up here somewhere. For a lower free stream velocity, the boundary layer would be down here. Alright, so the gradient is increasing for a lower one, and we'll have a higher flux in that case, or higher heat transfer. Lower heat transfer for the larger boundary layer. Based on your sketch of the velocity, will this induce the larger convective heat flux? Based on your sketch, which velocity condition will induce the larger local convective heat flux? Okay, so we just said that the one with the smaller or the larger velocity will have the larger heat flux. Okay, so that's just thinking about some of the physics. Let's look at the next problem I assigned was, let's look at number 3. So this is very much, you may already notice, like chapter 2 when we were talking about conduction. In that chapter they give you solutions for the temperature field and ask you to do some analysis with it, and they talk about how to solve for those solutions later on. So that's what we're doing here in chapter 6. They'll give us some information about the temperature field and then ask us about heat transfer coefficients and such. And then in chapter 7 we'll learn how to solve for those. So a particular application involving airflow over a heated surface, the boundary layer temperature distribution is approximated with this. Right, so Ts is the temperature of the surface, and then there's T ambient is the free stream. They give us a Prandtl number here. So this temperature, that T right there, that's T as a function of Y. They're giving us the profile distribution at a particular X location. So Y is the distance normal to the surface, and the Prandtl number is actually defined as, Prandtl number is nu over alpha. This is the momentum diffusivity, kinematic viscosity divided by the thermal diffusivity. So alpha is K over rho Cp, and this is equal to mu over rho. So if you substitute those values, the rho's can cancel, and so it could look like the Prandtl number could be C sub P times mu over K, although you don't normally see it that way. You normally see it given this way as mu over alpha. Okay, so for this airflow, for air, it's approximately, the Prandtl number is approximately 0.7. That's a dimensionless quantity as well. The Prandtl number is dimensionless. Okay, so they give us that Prandtl number that shows up in there is 0.7. If the temperature of the ambient and the surface temperature are given, so T surface is smaller, so this is a heating situation, and then they give us a U0 over nu combined, because that shows up together in the equations there. What is the surface heat flux for this problem? So what they're giving us, they're giving us this. They're giving us T as a function of Y, and then they're saying down here, what is the flux? What is Q double prime going into that fluid if they give us that profile? Right, so what we would do is, and let's think about an energy balance, just like we did before, right on the fluid layer, right here, that's not moving. So the conduction is now balanced to convection that's leaving on the other side. So Q double prime, I'm going to write the energy balance over here. That flux is equal to minus K of the fluid, the partial of T with respect to Y at Y equal to 0. So that's what's conducting through that bottom layer down here. This is Y equal to 0. Y is 0 on the surface. Y goes up as you go away. Right, so that's got to balance H times Ts minus T ambient. This, right, the fluid at that location is 300 K. So that is at 300 K for air. So that's a value that you can actually go and look up what that value of K is. H is unknown. They don't give us an H in this problem. They actually gave us the temperature profile itself, effectively gave us more information. This slope, however, we're given the temperature profile, so this we can evaluate. I just put, we can evaluate that with the given profile. Right, so take this equation, solve that for T, right, so take the temperature difference to the other side, then take this to the other side, so I'll go ahead and do it. T as a function of Y then is going to be equal to, take that temperature to the other side, this on the right hand side is 1 minus e to the power of minus Prandtl number U ambient, sorry this is getting crowded there, over nu times Y, all of that in that power. And then I have to move that minus over to the other side, so plus T surface. So that's the function. You can take a derivative of this exponential function. Or take a derivative, that won't have an effect. This won't have an effect. You only have this exponential term to take a derivative with. Right, so the partial of T with respect to Y will be equal to, we only need to worry about this term, minus times this. So derivative of an exponential function would be the derivative e to this again times the derivative of this, which will be derivative with respect to Y. It's just that constant out front. So that'll be a minus. And then those two minuses are going to cancel. So those minuses are going to actually turn into a plus. Right, and then I have that constant Prandtl U ambient over nu. That's that constant value there times this again, times e to the minus Prandtl U ambient over nu Y. Okay, now evaluate that at Y equal to 0. If I put a 0 at this location, anything to the 0 power is 1. So this is now equal to T ambient minus Ts Prandtl number U ambient over nu. Right, so just the constant values, right? So that actually now can go in place right there. Okay, so you can use that to evaluate the flux. The final answer for the flux is Q double prime is, I think this is probably on your page there, your assignment sheet. Minus 9205 watts per meter squared. It's negative because it's actually heating the plate in this case. Let's see, number 4. Water at 25 degrees C flows over one of the surfaces of a steel wall. It's going to be at 40 degrees C. The wall is 0.35 meters thick, and the other surface is 100 degrees C. Steady state conditions exist. The convection coefficient associated with the water flow is to be determined. What is the temperature gradient in the wall and in the water that is in contact with the wall? Okay, so we have a situation for number 4. That is our steel, AISI 1010, right? So the distance across that is L is equal to 0.35 meters. Let's call this the top side where we're exposed to the fluid. T ambient is at 25 degrees C. That surface temperature is 40 degrees C. Right, so there's a heat transfer going that way. This side over here is, let's call that T bottom, is 100 degrees C. Right, so there is some heat transfer by conduction through the steel, right, and this is all in steady state, so that will balance the heat transfer by convection away on the other side. So it's asking, let's think about this first. Let's get the temperature gradient in the wall. In the wall, the gradient means dt. It doesn't depend, it's steady, so I can make that a full derivative. dt dy instead of a partial, make that a full. dt dy for the steel is equal to Ts minus Tb divided by L. Right, the temperature gradient is going to be linear if it's steady, so it's the temperature difference divided by L. So that wasn't hard to come up with. And then we can think about in the water. Let's do an energy balance to figure that out. In the water, minus K fluid times dt dy. We're going to do an energy balance. That is what's happening in the water that's not moving right here. Right, so that's going to balance what's conducting through the wall. So that's going to be equal to minus K of the steel times dt dy in the steel. So in this case, I'm doing an energy balance of the conduction between these two. And so this is of the fluid, right? That is, evaluate that at what's called the film temperature. T film is equal to the average T ambient plus T surface over 2 is equal to 32.5 degrees C. And so K of the fluid then is equal to 0.62 watts per meter K. Over this side, look up K for steel. K steel is equal to 61.7 watts per meter K. And this is at T average is equal to 70 degrees C, the average between the 40 and the 100. Alright, okay, so that's known, right? We can put that here. The only unknown in this equation is this one, so solve that for dt. Bring this over here, solve that for dt dy of the water. It comes out to be minus 17.06 degrees C per millimeter, so that's a very, very large gradient. That's the gradient in the water here. The gradient in the steel, I have a number for that. I don't have a number for that to share with you. I'll let you compute that. And then lastly, we have to find H. To find H, now let's just do an energy balance that couples this with H. So we'll end up with minus K fluid dt dy of water is now equal to H times T surface minus T ambient. Alright, solve for H. H ends up equaling 705 watts per meter squared K. So for this one we found the gradient, assuming that it's constant through this steady state one-dimensional wall here, delta T over L. And then we did an energy balance on the surface, the conduction out of the steel into the first layer of the liquid that's not moving, right? That's conduction as well. We use that to get the temperature gradient in the water, right? Different than the temperature gradient here. So the gradient, so this is two different. There's the temperature gradient and the temperature field in the steel and the temperature field in the liquid, or yeah, in this case the liquid, are different. And then we can do an energy balance again to solve for H. And you can either put the steel here, or you can either put K steel dt dy of steel here, or you can put Kf dt dy of the water here. Either one works in the steady state situation. You can do that in general too for any energy balance, any surface energy balance as well, depending on what information you have and what analysis you're working on. Okay, number 5. Laminar flow over flat plate, the local heat transfer coefficient H. So this is how they distinguish H bar from H as a function of X. So they'll say Hx sub X is the local value. They'll put a bar over it to be the average value. So just some notes on nomenclature there. So they're saying that the local varies with X to the minus 1/2 power. So very, very close to how the boundary layer thickness varies. So X is the distance from the leading edge of the plate. What is the ratio of the average convection coefficient between the leading edge and the location X? Okay, so we have, here's the leading edge, X starts, X equal to 0 at the leading edge. Okay, so as we move down, so let's go down to here, that's at location X, at X, right? At that location right there, there's an H value, right? So right there, there's an Hx value. Between 0 and up to that point, there's an average value. So they want a general expression for the ratio of those two for any particular X it happens to be. What's the local at the end in comparison to the average from the leading edge all the way up to the end? From what we've talked about before, we would expect this Hx, so this local value of H, to be decreasing as X increases, which is the case because it's proportional to X to the minus 1/2. Okay, so what do we know? We know H, the local value of H, is equal to a constant times X to the minus 1/2. And if I want to figure out what is H bar, then we have to integrate from 0 to X. We're going to integrate Hx dx and then divide that by the distance from 0 to there is X to get an average value. So we simply have to take this and put it in place right there. The constant is going to come out front, so this will be C over X. If I take that, put it here, and then I'm left to integrate X to the minus 1/2 dx. So if you integrate this, this is 2x to the 1/2 after you evaluate the limits from 0 to X. So now the X in the denominator is going to cancel with one of these, so I'll end up with, in the end, 2 times C times X to the minus 1/2. Right, and so this is just Hx again. Right, so H bar is actually equal to 2 times the local measure at the end. So the average between there and there is twice the value of h here. And you would expect the average to be higher because h is constantly decreasing. If I were to draw this, it would look like there's h decreasing as you move over to the right. So the average is going to be twice of what it is over here. And it turns out that that's the case for any distance. It doesn't depend on x coincidentally because of that variation. Okay, so there's some hints for your homework if I didn't accidentally do your homework. Okay, so next let's continue our discussion here. Let's see, let me find some notes. Okay, I'm going to go ahead and continue on. I know it's been 50 minutes already, but you can pause, take a break, do as you want. I'm going to go ahead and complete the discussions of Chapter 6. It's going to take us another 15 minutes. We've already in the homework started thinking about a surface energy balance, so let's do that again. This is the thermal boundary layer, so this would be the temperature field up above, T ambient far away, T surface as we get close to the wall, and there's a transition between the two through the boundary layer. At some point the flow is going to become turbulent, at which case the boundary layer is actually going to get larger like this, and there'll be some more mixing and different physics going on here, and there is a transition. We're going to talk about all these details a little bit later. What I want to focus on here is the energy balance right here on the liquid layer again. On the liquid that's not moving where the velocity is 0 there, the flux through the surface is h times the temperature difference, and then which is also equal to what's conducting through that surface. So minus k of the fluid in this case times the partial of t with respect to y at y equal to 0. So that's the conduction in the fluid that's touching the surface and not moving. Again, that's k of the fluid, not k of the solid. Alright, so let's use this, solve that for h. Just take delta t to the other side. In order to solve for h, which is the problem of heat transfer, correct? That's why we're studying convection. All we really need to know is what is the partial of t with respect to y at the surface. And we substitute into this equation. Well, you got to know these other parameters too. But let's scale this problem. We've talked about scaling before. Let's take this and make it dimensionless. So we're going to scale the y by a length L. So ultimately we'll have a y star. Y star is equal to y over L. So y star is dimensionless. We're going to scale t by this temperature difference. Okay, so we've talked enough about it now that I think you guys know enough to say, well, what this means, the end result is everywhere I see a y, I'm going to put an L out front and turn that into an L star. Everywhere I set a T, I'm going to put a T ambient minus TS out front and make that a star. So that's the end result of doing the substitutions to scale this. And so there's my temperature gradient that's turning this into a T star. There's the L that's turning that Y into a Y star. So we'll just move those out front. These T's cancel with that, along with that minus sign. Right, now let's take the K fluid to the other side and take the L to the other side. You end up with HL over K of the fluid is equal to the dimensionless temperature gradient on the surface. So this has no units. This then therefore cannot have any units. This is the Nusselt number, HL over K of the fluid. So this differs. Think about this in comparison to the BO number, HL over K, you're familiar with. Right, that BO number is associated with a completely different physics, and that would be K of the solid for the BO number. So Nusselt number looks exactly the same, except it comes from this scaled surface temperature gradient in the fluid. So that's K of the fluid. So that's the difference between the two. So that'll be the Nusselt number and a dimensionless parameter. That's kind of our motivating factor for doing our correlations in terms of dimensionless parameters. The dimensionless heat transfer coefficient is the Nusselt number, HL over K. And so, without actually doing this, I'm just trying to give you a little bit of the details enough so that you can believe them. You can take those equations that we had earlier. I gave you the Navier-Stokes equations and the energy equations and the boundary conditions and all of that, and we can scale those just like we did that one surface energy balance. If you do that, you can take H, which would depend through that flow field on all of these physical parameters, and even H bar on all of these physical parameters. The only difference between the two is I have H as a function of position, and here H bar is an average over something of size L. All of those, this can be expressed in terms of dimensionless parameters, so we'll use the dimensionless parameters that comes out of scaling the equations. There's a connection between scaling and Buckingham pi, right? That's effectively the same problem. And so what we're going to do is say the dimensionless H is actually the Nusselt number, defined as Hx over K. That's K of the fluid. It turns out that it's only going to depend on the Reynolds number and a Prandtl number. The Prandtl number is the ratio of the diffusivities, momentum diffusivity, or this is kinematic viscosity relative to the thermal diffusivity. And you remember the Reynolds number, rho times the velocity times x over mu. Right, so it turns out we're going to use x as our distance when we're evaluating a local heat transfer coefficient. So if you take that rho, put it in the denominator of the denominator here, this becomes a kinematic viscosity here. So that's mu and that's nu. So this is a little bit easier, one less property to deal with if you can look up kinematic viscosity instead of these two properties. It's the same. And then for the Nusselt number for the average H, I'm going to use a nomenclature to call this L instead of X here. The textbook doesn't necessarily do that. I think it makes it clearer that this is an average H over a length L and not a local value at X. It's the average between 0 and X, or between 0 and L. So that's going to depend on the Reynolds number based on L and a Prandtl number. So this is the, put a little bar over this Nusselt number, is the dimensionless H bar. Okay, so this, I'm going to tell you now, this Nusselt number bar is not the average of this Nusselt number. Instead, it's effectively a separate correlation for H bar. So let's go ahead and write that out to the right here. Nusselt number bar is actually not equal to the average, right, from 0 to L. Is actually not equal to that. Instead, it's just our notation to indicate that this is the scaled H bar. So be careful with that later on. So all of these Reynolds numbers and even the Nusselt number have properties in them, right? And the properties depend on temperature. So when we do our correlations, we're kind of doing an approximation anyway. Our empirical correlations, we're running experiments. There will be some amount of error or uncertainty associated with those. We're going to evaluate these properties at what's called the film temperature, which is the average between the ambient temperature and the surface temperature of the film. So it's the average over the full range of variation for the temperature throughout the thermal field, or inside the thermal boundary layer. So it's the average temperature inside the thermal boundary layer. Maybe that's the easier way to say it. T surface plus T ambient divided by T is T film. So this is the called the film temperature. Okay, so when we evaluate the Reynolds number and the Prandtl number and the Nusselt number, and you need those property values, you have to calculate the film temperature and then go interpolate from the tables to get appropriate values to then substitute into these dimensionless parameters. But ultimately, the solutions that we're going to use in Chapter 7 will be empirically determined correlations that looks like this. The Nusselt number will be a function of the Reynolds number and the Prandtl number, so we'll say that they're proportional to the Reynolds number to some power and then the Prandtl number to some power. And the same thing for the average case, right? Only these coefficients will be different. So what we could do is go run some experiments, correlate the data, basically do a statistical analysis and do a regression through the data to figure out what are the values of those coefficients. And again, all of the fluid properties then are evaluated at the film temperature. And as an example, if you go to table 7.9, we'll look ahead a little bit into chapter 7. Right, here's a long list. You'll have this available. Well, you'll have an open book test, so Here's a long list of some of the coefficients, right? So here's the Nusselt number, the local Nusselt number, a constant times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. This is the case for flow past a flat plate in the laminar region, so long as the Prandtl number is greater than about 0.6, which is mostly true. For air, it's 0.7. So for most cases, this is going to hold over the laminar portion of flow past a flat plate. And you have many other correlations here. You have correlations also for the boundary layer thickness, also for the skin friction coefficient. So this is the scaled surface stress, shear stress on the surface. Okay, so we're going to be looking at solutions that are in terms of dimensionless parameters. So let me give you those dimensionless parameters. For those involving the flow field and the interactions at the surface are all we really care about for the heat transfer problem. Delta, the scale delta is just delta over x, x being the distance from the leading edge. The surface shear, we're going to scale that by dividing by 1/2 rho U ambient squared. This has units of a shear or a force per unit area, so this becomes dimensionless. This is called the friction coefficient, and so that's the local shear stress scaled, so in dimensionless form. If you do it in terms of an average, right, we just take the average shear, divide it by the same scale, and then we just put a bar over the top of it to indicate the average shear. So once again, we would say that this CF bar is not the average of that. Instead, this is just to indicate this is the correlation for the average value there. Okay, so those are typically correlated as functions of just the Reynolds number for the flow field up above. For the thermal field, the thermal boundary layer, delta sub T, is scaled by the actual momentum boundary layer. So delta sub T over delta, and it turns out that that is theoretically equal to the Prandtl number to the minus 1/3 power. And remember what the Prandtl number is, a dimensionless parameter over here. So I'm effectively giving you the correlation for that one. H is Hx, so the local H is Hx over Kf, that's the Nusselt number, and then the average Nusselt number is HL over K. So these will be empirically determined and provided as a function of the Reynolds number and the Prandtl number. And so we got different correlations depending on if the flow is turbulent, laminar. If there's internal flow, that means there's effectively no boundary layers, as viscosity is important everywhere. Or if it's external flow, then there's boundary layers. All of those things are going to vary those correlations. And so what really our convection problem has turned into is how do you find the right correlation or the best correlation for the problem you're looking at. Okay, I'm going to work one last example, and that's going to conclude our discussion on Chapter 6. Experimental results for heat transfer over a flat plate. They provide us with this correlation, right? Local Nusselt number in terms of a Reynolds number and a Prandtl number. So as defined previously, and x is measured from the leading edge of a plate, obtain an expression for the ratio of the average heat transfer coefficient h bar to that of h. So they don't tell me, they don't give us the average, they don't give us Nusselt number average as a separate correlation, they only give us the one. Alright, so let's see, part A, Nusselt number based on x is equal to hx times x over kf. So remember this h sub x, that's just the textbook's way of saying h. That's the local heat transfer coefficient. Reminding us it depends on h. It depends on x. So times x divided by k of the fluid. Okay, so I'm going to take this and put it in place here. We can solve that for h. That'll give us an expression for hx. So the local heat transfer coefficient is equal to kf times 0.04 Reynolds number to the 0.9 Prandtl number to the 1/3. Divide that by x. Right, so if you take k the units of K, watts per meter K, divide that by another length meter, you get units of H, right? Watts per meter squared K. This, all up there those are all dimensionless parameters. So that gives me an expression for H at any particular location. Let's call this X, distance from the leading edge. So this is the flat plate. Right, go down here to this location. So we've already worked a similar problem like this. There's H at that location right there. I'm going to call this L. We're going over a distance from the leading edge out to there is L. So from there to there, we're going to have an H bar. It wants us to come up with an expression for that H bar between there and there. What it gave us was H as it varies across. Right, okay, so the definition of an average H bar is equal to 1 over L integral of 0 to L H dx. We're going to integrate from 0 to L and then divide by that length L. Right, okay, so we can take our expression up here and substitute. This is going to be equal to Kf over L, 0.04 Prandtl number to the 1/3, that's a constant, times the integral from 0 to L. The Reynolds number depends on x, so I can't take that outside the integral, divided by x dx. Alright, so that Reynolds number that shows up in there is U ambient times x over nu. So there's another x dependence there. So I have x to the 0.9 divided by x leaves me with x to the minus 0.1. And then the rest of that constant, that to the 0.9, could come out front. So now I have Kf over L, 0.04 Prandtl number to the 1/3, and then also out front of that is U ambient over nu to 0.9 times the integral from 0 to L of x to the minus 0.1 dx. So now it's just a matter of evaluating this, right, and then substituting. So if I add 1, I get x to the 0.9 divided by 0.9. So this is going to be x to the 0.9 divided by 0.9 evaluated from 0 to L. So L to the 0.9 divided by 0.9, which is equal to L to the 0.9 divided by 0.9. So that goes in place here. So I got Kf over L, 0.04. Notice that I have U to the U ambient over nu to the 0.9, and then a L to the 0.9. If I combine those together again, I get a Reynolds number to the 0.9. Then I'm going to put my Prandtl number to the 1/3. Then I'm left with that 0.9 in the denominator, so I'll leave that. Okay, but notice that that is actually a repeat of the given up above. Right, that's just the local heat transfer coefficient. Alright, so that, if I put all that together, it's a local heat transfer. So H bar over H is actually just equal to 1 over 0.9, right, or 10 over 9, however you want to write that. So there's the ratio. That's the answer that this is looking for. Turns out that the average is equal to 1 over 0.9, 10/9 of the local heat transfer coefficient in this case. So let's see. So H bar is equal to, take the H to the other side, 10/9 of H. So H bar is just, in this case, a little bit larger than H. Right? Just a little bit larger than 1. So H is actually decreasing as X increases. This H is decreasing. So the average between 0 and some value where this is decreasing is always going to be larger. Okay, so part B, it says obtain the associated correlation for the average Nusselt number. So now we need to come up with the average Nusselt number. So this is defined as H bar L over KF. Right, and we now have the expression for this, right? H bar, this is up here, this is H bar. That H bar now can be substituted here. Alright, so that's going to be equal to KF 0.04 Reynolds number L to the 0.9 Prandtl number to the 1/3 over L, that has a 0.9 in it, and then I have an L over KF. So all of that is the H bar, excuse me. So these two can be combined, and then let's see, that and that and that and that are going to cancel, so we'll end up with, if a 0.04 divided by 0.9 is 0.0444 to eternity. So there's the correlation, the equivalent correlation for H bar in comparison to, let's compare to what they gave us, the Nusselt number based on X. Sorry, don't put a bar on that one. The local Nusselt number is 0.04 Reynolds number based on X to the 0.9 Prandtl number to the 1/3. So the constant just changed a tiny little bit, dividing by 0.9. Okay, so what you could do is, if you evaluate, take 1 over L, 0 to L, take this expression, right, and substitute it in here to calculate the average Nusselt number. If you do the work for that, I'm not going to show it to you. If you do the work, you get 0.02105 Reynolds number L to the 0.9 Prandtl number to the 1/3. Alright, this is a different answer. This is not that up above. Alright, what we had to do is calculate H bar and then use that in this correlation. You cannot take the Nusselt number expression, local, and integrate that to get the average Nusselt number. This doesn't work, right? And so this, I'm going to point out again, that is not equal to the integral from 0 to L of Nusselt number X dx over L. You can't do it that way. Right? This is different. Right? Not the same. Okay, so read Chapter 6, peruse those sections that I told you to look at, so you can get an idea of the communication that they're doing, and maybe even some understanding of the scaling and dimensionless parameters that show up. And then we're going to move on to Chapter 7 next time, where we'll look at some solutions and empirical correlations and how to do some calculations for H. Okay, so that concludes Chapter 6. I'm going to go ahead and share this with you. I know that it's still Easter weekend, but I'm going to share it with you, and whenever we get to questions, whenever you watch this so you can get to questions, that'll be fine. We'll talk about it next week.